Hello everyone, welcome back to a new video. This time we're going to be solving some physics questions. I have a bunch of questions prepared. We're just going to solve them. So the first topic is circular motion. You're going to be asked questions like these. I have a couple questions ready. So these are different types of questions that I think are important. Just a couple. I'll get to the A-level questions, but these will also come up in the exam. So let's begin. So first of all, we have an object rotating in a conical inside a cone like this. I'm not gonna solve this with the values. I'm just gonna solve it with random variables. So basically, you can model. Let's model this section of the thing. So we have this. And the angle is alpha, let's say. And I'm gonna say this point right here is our object, and we need to. So in questions like these, what we need to do is we need to draw all the forces acting on the object, and then we need to find the components of those forces that are in the direction of the centripetal force, add them up, and equate them to the centripetal force. So at this point, we have two forces, one which is gravity, and the other which is the normal force, like this. And if we draw axes like this, we want to find what the net force in this direction is equal to, because that's the direction the object is rotating in, like this. So we need to find that force. Now, notice how the gravity doesn't have any component. So we just need to find the component of the normal force that's in this direction. So we need to find this force right here. So like this and this. We know this angle is alpha. So this angle must be 90 minus alpha. So this angle is alpha. Yeah. Then, if this has magnitude n, this has magnitude n cosine alpha, and this has magnitude n sine alpha. We want to find n sine alpha, and notice how the object doesn't go anywhere in the vertical direction, so the net force in the vertical direction is 0. So n minus cosine alpha must equal mg, or n cosine alpha must equal mg, and we want to find what n sine alpha is. So this means n is going to be equal to mg over cosine alpha. So we multiply that by sine alpha, and we get that this is equal to mg times the tangent of alpha. Okay, so now we know that this is equal to mv squared over r, or it's equal to m omega squared r, depending on what you need. Here we want to find the angular speed. So the angular speed is just going to be, you can find by solving the equation mg tangent alpha equals m omega squared r. So the m's cancel. Omega squared is equal to g tangent alpha over r, and omega is equal to the square root of that. Here you can put in the values if you want. I'm not gonna, because it's just TI. It's just a calculator job. Like, I'm not gonna do that. Anyway, that was the first question. So in questions like these, just this force can be friction, can be tension, it can be the normal force in this case. It can be a lot of different things. You just need to find the forces and find the components in the direction of the centripetal force. All right, so here we have an object that's released from point A to the friction surface, and we want to find the reaction force at B. So again, let's draw all the forces acting on the object at this point. So we have the gravitational force mg, and we have a normal force n. Now notice how n is already in the direction of the centripetal force. However, there's also a component of mg that's in the direction of the centripetal force. So let's find that. So if this angle is 30, this angle is 60 degrees. So mg cosine 60, mg cosine 60 or mg halves is the direction of this, is the magnitude of this force. So we have two forces acting on in the direction of the centripetal force, which is mg halves plus the normal force. So that I'm going to draw it like this. So that is the all force acting on the Earth, and that should equal mv squared over r, because that is the centripetal force. Now, how do we find mv squared over r? Well, we're going to have to use the conservation of energy for that. Here, the object isn't doing uniform circular motion because the centripetal force is changing as the velocity is changing. So this is not uniform circular motion, but we can still find this value by doing the conservation of energy. So here, the object has a potential energy of 2 mgr. Here, it has a potential energy of, well, let's find the height. So this length is r, so this length must be r halves, and this length is r as well. So this length is 3r halves, so the object has mg times 3r halves of potential. So the potential difference is potential energy difference is gonna equal the kinetic energy at this point, because here the object is released at rest, so it has no kinetic energy. So the difference in the potential energy, so that's 2 mgr minus 3 mgr divided by 2. It's gonna equal, so this is 4 over 2, so we're gonna get mgr over 2, and this is gonna equal 1/2 mv squared over 2. Or 1/2 mv squared. The over 2's cancel, and we get that, and then we can divide by r to get that mg is equal to mv squared over r. So now mg halves is plus the normal force is equal to mg. That means the normal force is equal to mg halves. That's it for this question. Yeah, that's it. So here we have an object that is released from point A. Find from which height the object will leave the semicircular. Okay. So there are a lot of different questions that have that ask this basically, that when will the object leave the semicircular office, or when the object will leave the circular path. So in this case, the force that's causing is the centripetal force is this normal force right here, as well as the source of gravity, like this. It could be the tension, for example, on a string, and you could be asked when like an object flies off a string. That happens when the tension on the spring is equal to 0, because at that point the object isn't on the string, so the tension must be 0. Here, for example, if the object leaves the semicircular surface, then the object isn't touching the semicircular surface, and hence the normal force must equal 0. For example, it could be a question like, for example, you could have a circular path like this, and the object's going like this, and you could be asked to find when it falls off, and that's again when the normal force is equal to 0, at which point the object ceases contact with the surface. Anyway, so this is we need to do the exact same thing here. We need to find out the components of these forces that are in the direction of the normal in the direction of the centripetal force. So we have the normal force in the opposite direction here, and let's call this angle right here theta. So then this angle right here will be theta, and you can see that this force right here, or you can see that we can compose gravity into two forces like this. This force is the tangential, like falling force for the object. I guess the tangential acceleration, you could say. The tangential force. However, we need to find this force right here. Hold on. We need to find this force right here, which has magnitude mg cosine theta. So the net centripetal force is mg cosine theta minus the normal force, and we know that's going to equal to mv squared over r. Now we want to find the theta such that Okay, we want to find the theta such that this normal force is equal to 0. So if this is equal to 0, that means mg cosine theta must equal mv squared over r. Again, to find what mv squared over r is, we can use the conservation of energy. So at this point, the object has a potential of, at A, the object has a potential of mgr. And it's at rest, so it has no kinetic energy. So its total energy is mgr. Here, it has a potential energy of, well, this height right here, mg times this height. That will be, so if this length is r, this length is mg, no, it's r times cosine theta. So this length is r cosine theta. So it has potential mg r cosine theta. So the potential energy difference is going to be mgr minus mgr cosine theta, which is equal to mgr times 1 minus cosine theta. And that's equal to the kinetic energy at that point, which is 1/2 mv squared. Now, from this, we need to find what mv squared over r is. So we can divide by r and multiply by 2 to get that mv squared over r is equal to 2mg multiplied by 1 minus cosine theta. So let's put that into this equation right here. We'll get mg cosine theta equals 2m, I'm going to expand this, 2mg minus 2mg cosine theta. I'll also cancel out the mg's. So we'll get that, and then you can throw cosine here. So that 3 cosine theta equals 2, and that cosine theta equals 2 over 3. From this, you can find the angle if you want. We don't need to, because we're asked to find the height at which the object leaves the surface. And here h is r cosine theta. So it's simply equal to 2 over 3r. And again, these are simple questions, but these are important. You need to know how to solve these kinds of questions. And any question that will come up that's similar to this, well, it's similar to this, of course. So if you know how to solve these, you can probably solve them. You can also be asked, for example, an object that's swung around with a string, and you need to figure out the force of gravity acting on the thing and the tension force and whatnot, like a vertical tension question. Doesn't matter. Anyway, let me get to the A-level questions now. All right, everyone. So I'm gonna solve an A-level style question on circular motion now. This is a pretty simple question, but I just want to solve an A-level style question for this. So we have this like carousel thing. Apparently, it's called a fairground ride, I guess, moving at a constant angular speed. So it's doing uniform circular motion, and it makes a complete rotation in 6.8 seconds. So the period is 6.8 seconds. And it's moving in horizontal circles. We have a mass of 25 kilograms at this point, and the length of the chain is 6 meters, and we have it makes an angle with the vertical, which is theta A, which is 40 degrees. I mean, to show the tension, okay, is 320 newtons. So again, we should draw all the forces acting on the object. So we have the force of gravity, and we have the tension force. Now, this has a horizontal component like this and a vertical component like this. So since the object isn't moving in a vertical component, then the vertical component of the tension must cancel out the gravity force. This horizontal component is going to be the centripetal force. So let's figure out what the vertical component is. If this is theta, then this vertical component is going to be ta cosine theta A. So ta cosine theta A equals mg. So let's know what ta is, which is mg over cosine theta A. That's going to be 25 kilograms times 9.81 meters per second squared divided by the cosine of 40 degrees. which let me put into my TI real quick. We get 25 times 9.81 divided by the cosine of 40, which gives us 320.151 newtons. All right, which is indeed approximately 320 newtons. So next, it wants us to calculate D. So here we're gonna have to use the fact that this force right here, TA sine theta A. So TA sine theta A, that's gonna equal the centripetal force, which is mv squared over r. That means that if we know the period, it's gonna be easier to find the angular speed. So it should be easier to say this is equal to m omega squared r. And well, what exactly is r? We can find that out by, okay, so r is going to be the radius of the circular motion. So the distance between A and the vertical axis like this. So now we know this distance right here, that's L sine theta A. And this distance right here is going to be the distance between this point and to the vertical axis, which is D. So we can find D from that. We know that R is going to be L sine theta A plus D. So we need to find D from that. So R is going to be TA sine theta A over m omega squared. To find omega, we can just, we know the period. So the omega is going to be how many radians the object travels in 1 second. So it travels 2 pi radians, which is a complete rotation, in 6.8 seconds. So omega is going to be 2 pi divided by the period, which is 2 pi over 6.8, which is, it's 0.923998 radians per second squared. We can plug everything here into this formula right here. It's going to give us 320.151 newtons times the sine of 40 degrees divided by 25 times 0.923998 squared, which gives us, let me see, 320 times 0.151. I'm just gonna get the previous answer. There we go. Multiplied by the sine of 40 degrees divided by 25 times this value right here, which is squared. Okay, that makes 9.64141 meters. Now we need to find D. So D is going to be R minus L sine theta A, which is 9.64141 minus 6 meters. I think, yeah, 6 meters times the sine of 40 degrees, which is going to equal, let's see what's going to equal, minus 6 times the sine of 40 degrees. That will equal 5.78469. We have been given the values to 2SF, so I'm just going to write the answer in 2SF. It is 5.8 meters. So we have a couple questions here, but I don't think these are that important. These are just annoying. So yeah, I'm not gonna solve these. If you want, this is the January 24th Physics 3 paper, the 3rd physics paper. You can solve it if you want. I'm not gonna. So yeah, that's it for this question. Alright everyone, now let's continue with some rotational dynamics questions. So I'm going to solve A-level questions that we have solved in class for here, because there's going to be a really high chance like these questions appear in the exam. So anyway, this question is about a wheel that is at rest on a ramp and then is released and uniformly accelerates without slipping. And the important part here is that it's held at rest at the beginning. So at time t1, it has completed less than 1 rotation, and R, the point R, has moved from here to all the way here. And we're giving the angular acceleration. And then, okay, so it asks us to find that how much x has rotated by here. So x will have rotated by this angle right here. Now notice here it doesn't say it's not drawn to not to scale. It's drawn not to scale, like it does in most questions. This means this has been drawn to scale, and you're gonna have to use a protractor to measure this angle right here. Now you need a protractor in our exam, so there's a really high chance like that this specific question might appear in the exam. So yeah, just letting you know that. And if you measure this, I think this comes to about 150 degrees. So if this 150 degrees, that's pi, that's multiplied by pi over 180 is gonna equal, let's see, 150 times pi over 180 is equal to 2.61799 radians, which approximately equals 2.6. And this is at T1. And now we need to find what T1 actually is. Now here, we need to use that the angular acceleration. We need to use that the theta is going to be the initial angular velocity times t plus 1/2 times the angular acceleration times t squared. Now we know that it's being held at rest initially, so this value is 0. So it's simply theta is simply going to be equal to 1/2 alpha t1 squared. This is similar to the kinematics equations, by the way. So if you can memorize it from that. So then if you solve for T1 is going to be equal to, it's going to be equal to 2 theta over alpha and square rooted. So that's going to be equal to 2 times 2.61799 radians. 99 radians divided by 3.6 radians per second squared, which is going to give us the square root of 2 times that divided by 3.6, which is going to give us 1.206 seconds. Now, the quantities have been given to us in 2SF, so I'm just going to write this as 1.2 seconds. And now we need to find the angular speed of x as it completes its first rotation. So here we can figure it out using time. So you can find the time it takes to complete a 2 pi radian rotation, and then plug that time in as omega as alpha t, which would give you omega. But I'm gonna use the timeless formula. So here, the final angular acceleration or angular velocity is going to equal the initial, or the final angular velocity squared is going to equal to the initial angular velocity squared plus 2 times alpha times the angles of the radians rotated, which is theta. This is similar to the kinematics equation of v final equals v initial squared, or v final squared equals v initial squared plus 2ax. It's exactly that in a rotational form. We know. Hold on. Yeah, we know that the. Oh God. We know that the initial angular velocity is 0, so we can simply remove that. So the angular velocity, the final angular velocity, is simply 2 alpha theta, which is going to equal to 2 times 3.6 times the theta of a full rotation, which is 2 pi for the first rotation, of course. For the second rotation, it would be 4 pi. Anyway, this is square root of 2 pi, 2 times 3.6 times 2 times pi, which is equal to 6.72599 radians per second. Again, I'm going to give it to 2SF, which is 6.7 radians per second. Okay, so now let's continue with this question. So here, you have 2 disks, X and Y, and they're rolled. They're allowed to accelerate down a ramp, and we need to compare their angular accelerations. The important point here is that they have the same mass and the same diameter. Now, if you put these guys along a ramp, you have to think about what actually rotates them. So, oh God. So the there's going to be a gravitational force at their center of mass, which has a translational effect in the direction of the ramp. And this translational effect is going to cause a friction force on the wheel that will cause a torque along the center and will cause it to rotate. So that is what causes the wheel to rotate. And since both y and x are made of the same material and have this, I think there's, I don't know, it's supposed to be made of the same material and have the same mass and the same diameter. I guess it doesn't matter, does it? Anyway, they have the same mass and the same diameter, so the friction force is going to be equal. So the torque that's rotating them is equal. So you can explain it in more detail, but the torques that are rotating them are equal. Now, this means that their moment of inertia times the angular acceleration is equal for both of them. Now, here's the thing. To compare the angular accelerations, we need to compare the moment of inertias. And now, looking at these disks, you might say, well, this is more filled in, so hence it has a higher moment of inertia, but that's actually false, because these both have the same mass, while in wheel X, more of the mass, like most of the mass, is concentrated on the outside, the outer rim of the wheel, while in disk Y, most of all of the mass is distributed equally for all radii. So if you think about the moment of inertia for a point mass, that would be mr squared. Here, this radii is distributed equally for all masses, while for all points, I guess. While in wheel X, for example, this point has a much higher radius, and hence there is a larger mass concentrated on the outside, hence the moment of inertia is higher. So Ix is higher than Iy. This means that alpha x must be less than alpha y, so that the torques are equal. And there we go, that we have compared the angular acceleration. You have to explain this, of course, in more detail for this question, but this is basically the general premise. All right, so let's continue with this question. This is a simpler question, but let's just quickly do it. So we have two rotating disks, and then they combine, and we're asked to find their final angular speed and their direction of rotation. So this is simply just the conservation of momentum, but the rotational version, so the conservation of angular momentum. So linear momentum P is equal to mv. So angular momentum L is equal to m, which is I, and v, which would be omega in rotational context. So this is the formula that we're going to be using. L equals I omega. And so Lx, so the initial total angular momentum is, it's going to be Ix plus omega x plus Iy times omega y. And when they combine, their moment of inertias add. So this will be Ix plus Iy times their final angular momentum. So we can simply divide by their moment of inertias. So the thing here is that they rotate in different directions, and angular momentum is a vectorial quantity as well as angular velocity. X rotates clockwise, so I'm gonna say clockwise is negative 48 radians per second, and anti-clockwise as 22 radians per second, or plus 22. This is just how it's usually. This is convention. Like anti-clockwise is usually positive, because if you do the right hand rule in this image, it will be upwards, and it doesn't matter. You'll get the same answer both ways. So this will be 1.2 times negative 48 plus 1.6 times 22 divided by 1.2 plus 1.6. Which is going to be, let's see, negative 48 times 1.2 plus 1.6 times 22 divided by 1.2 plus 1.6. That'll give us negative 8 radians per second. And negative is clockwise, so it'll be 8 and clockwise. So the answer is 8. That was a simpler question. Okay, so now let's continue with this question. You have a guy that's rotating a hammer like this, with increasing angular speed before releasing the hammer. Right, so the athlete starts from rest. That's important. It starts from rest and exerts a constant torque of 55 Newton meters for 7.1 seconds before releasing the hammer. And the average combined moment of inertia of the athlete and the hammer is 37 kilogram meters squared. I need to find the angular speed about the vertical axis at the instant of release. Okay, so we know that torque is equal to I alpha. And from that, we can find the angular acceleration. And then, if you know the angular acceleration, then since it's omega is going to be the initial omega plus alpha times t. And we know the initial omega as 0, so we can just write that. So from this, we can find alpha to be tau over I, which is equal to 55 Newton meters divided by 37 kilograms meters squared. And that's equal to, let's see, 55 divided by 37. It's equal to 1.48649 radians per second squared. And omega is going to equal to alpha t, which is going to be 1.48649 times the time, which is 7.1 seconds. That's going to equal 10.5541 radians per second squared, which is indeed approximately 11 radians per second squared. So that's nice. Next, we need to calculate the angular momentum of the athlete and the hammer at the instant of release. And we need an appropriate unit. Okay. So angular momentum, L, is the mass, the rotational moment of inertia. So I and omega. So we know I to be, this is going to be equal to 37 kilograms meters squared times omega, which is 10.5541 radians per second. So this is going to equal, let's see, that times 37, which equals 300.5 kilograms meters squared radians per second. You can also calculate this by multiplying torque by the time taken. So that would be 55 times 7.1, which is equal to indeed 390.5. I'm just gonna write this. So it's 390.5 with units kilograms meters squared radians per second. Okay, so from the instant the hammer is released, the athlete is no longer exerts any torque, and there is no external torque. And what happens to the angular speed of the athlete at the instant the hammer is released? So if you think about like this, the athlete is rotating. And once the hammer is flown off, it is no longer rotating. So the moment of inertia of the system decreases. But angular momentum must be conserved, so the angular velocity of the athlete increases. So we can write that as the hammer flies off, it is no longer part of the rotating system, and the moment of inertia of the system of the rotating system decreases. However, since no external torque is applied, the angular momentum is conserved. And hence, the angular velocity must increase. The angular speed must increase. You can write that in more detail if you want. Yeah, that's it for this question. I'm also just going to quickly solve this problem as well, because it might get confusing for some people. So here a mass falls on top of a disk and no external torque is acting. Now this tells you that angular momentum has to be conserved. So these it can be either B or C. Now the thing is, it sticks to the disk, and this means that rotational kinetic energy cannot be conserved. So the answer is B. Now, if you are asking why can it not be conserved, well, I'm not going to answer that. We can prove it mathematically. But if you think about the linear case, for example, if there are two materials and then they stick together once they collide, then you can be certain that this is an inelastic collision, because there's some energy lost. And if it's an inelastic collision, that means, the kinetic energy is lost. And this is exactly the same in the rotational case. Again, this is a super simple question, but I still want to solve it. So these all have the same mass, and we're asked to find which has the smallest moment of inertia. Now, the moment of inertia increases as the radius increases. So if these all have the same mass, then we want them to have more mass concentrated near the radius, so the moment of inertia decreases. And the one that has the most mass concentrated near the axis of rotation is B. So the answer is B. Yeah. All right, let's quickly solve this problem right here. So we have a solid sphere with radius 0.14 meters. The sphere as at the top of a ramp with 30 degrees to the horizontal, and initially at rest and released, and the frictional force produces a torque that causes an angular acceleration of 25 radians per second squared. All right, that's going to be important. So the mass of the sphere is 1.8 kilograms. So the moment of inertia of the sphere is that. We're asked to find what the frictional force F is. So now this frictional force will cause a rotation. That will cause this to rotate. Now, here's the thing. This will cause, so the torque applied by this frictional force is Fr. That's the torque. And that's going to be equal to I alpha. So F is simply I alpha over R. We can quickly calculate I as 2.2 over 5 times the mass, which is 1.8 kilograms, times the radius squared, which is 0.14 squared. That will be 2 over 5 times 1.8 times 0.14 squared. That'll be 0.014112 kilograms meter squared. So F is going to be to 0.014112 times 25 divided by 0.14, which will be 2.52 newtons. I'm just going to write 2.52. Right. Now it wants us to calculate the angular speed of the sphere 1.5 seconds after release. Now initially it's at rest, so the angular speed is simply going to be alpha times t. So that will be 25 times 1.5, which is 37.5 radians per second. Now we need to show that the sphere travels approximately 3.9 meters along the ramp in the first 1.5 seconds. So in the first 1.5 seconds, the amount it rotates, the amount of radians it rotates, is gonna be equal to 1/2 alpha t squared, because initially it's at rest. So that will be equal to 1/2 times 25, I think was, 25, times 1.5 squared, which is, let's see, 1/2 times 25 times 1.5 squared, which is 28.1225 radians. Now, the amount of distance it travels, if you think about, if let's say a point rotates by theta radians, then if the radius is r, then the amount of distance it has covered is going to be theta r. So the amount of distance x is just going to be theta r, which is going to be 28.125 times the radius, which is 0.14 meters. That's going to be equal to 3.9375 meters, which is indeed approximately 3.9 meters. You could also do this by dividing this value by 2 pi. So dividing this value by 2 pi, which will give you the amount of revolutions the sphere has done, and then multiplying that by 2 pi r to find the distance it has covered. Of course, it's going to be the exact same thing, but yeah. Okay, so next we're asked to find the reduction in the gravitational potential energy of the sphere in the first 1.5 seconds. So now, if the sphere has moved, let's say this is the central mass, if the sphere has moved how many? 3.9375 meters, then the reduction in its height is going to be that multiplied by the sine of 30 degrees. So h is going to be 3.9375 times sine 30 degrees. So mgh, so h is going to be 3.9375 times sine 30. And so mgh is going to be equal to, what's going to be equal to? It's going to be equal to 1.8 times 9.81 times 3.9375 times sine of 30 degrees, which will equal, let's see, 0.8 times 9.81 times 3. Whatever this value right here. That also multiplied by the sine of 30 degrees, which is 1/2. So you get 34.7642 joules. I'm going to need to 3SF, that's 37.8 joules. Now to calculate the increase in the rotational kinetic energy of the sphere. So the rotational kinetic energy is 1/2 I omega squared. Now, initially it had an energy R, I'm going to say. ER0 is equal to 0 joules because initially it was at rest. So ER final is going to be equal to simply 1/2 I times omega final squared, which is going to be 1/2 times, we found I earlier as 0.014112, 0.014112 times the angular speed, which is 37.5 radians, and that's squared. That'll be that will be 9.9225 joules. I'm just going to write the 3SF as 9.92. Alright, now, the sphere is now placed on a similar frictionless ramp State and explain how the lack of friction will affect the change in rotational kinetic energy. So this increase in rotational kinetic energy, I guess. Now, here's the thing. The thing that's actually causing this thing to rotate is the frictional force itself. So if there is no frictional force, they won't rotate. The sphere doesn't rotate. Meaning it doesn't gain any rotational kinetic energy because all the gravitational potential energy that's lost is going to be converted into translational kinetic energy. I'm going to be honest, I'm lazy to write. You can write that. Yeah, that's it for this question. That's it, I think, for rotational dynamics. Now let us get to gravity. All right, everyone. Now let us continue with some gravitation questions. I'm gonna again do the exact same thing and solve some A-level questions. Now, these questions usually require astronomical constants. So I have a couple of these, specifically big G, which is 6.67 times 10 to the negative 11, and the mass and the radii of the sun and the earth, which are all gonna be useful. All right. So now we have information about a comet, and we're asked to find that the gravitational force of the sun on the comet. So that gravitational force is going to be gmm over r squared, which is equal to, okay, that's going to be equal to 6.67 times 10 to the negative 11, which is g, times the mass of the sun, which is, what is that? It is 1.99 times 10 to the 30. 1.99 times 10 to the 30 times the mass of the comet, which is 2.242 times 10 to the 14th divided by the radius, or the distance between them, squared, which will be 8.758 times 10 to the 10 squared, which will give us, let me put that into my TI. So this topic is notoriously annoying with calculations like these, because like them, they take too long, but can't really do much about that. So 10 to the 30 times 2.242 times 10 to the 14 divided by 8.758 times 10 to the 10 all squared, blah blah blah, which gives us 3.87976 times 10 to the 12 newtons, which is indeed approximately 3.9 times 10 to the 12 newtons. All right. So next, we are asked to show that the gravitational force and data show that the comet is not in circular orbit. Now, as we are also told the comet is in elliptical orbit, but we need to prove that it's not in circular orbit with this gravitational force. Now, here's the thing. If an object was in a circular orbit, then the gravitational force acting on it, on the comet, would be equal to mv squared. So gmm over r squared will be equal to mv squared over r, which is the centripetal force. Because, yeah. So if the comet, was in a circular orbit, gmm over r squared would be equal to mv squared over r. Now let's calculate mv squared over r. So mv squared over r is going to be the mass of the comet, which is 2.242 times 10 to the 14 times the velocity of the comet squared. So that's 5.457 times 10 to the 4 squared divided by the distance to the sun, which is 8.758 times 10 to the 10. So that will be equal to, let's see, that'll be equal to 2.242 times 10 to the 14 times 5.457 times 10 to the 4 divided by 8.758 times 10 to the 10, which is equal to 7.62322 times 10 to the 12 newtons. However, so this means this is not equal with this force. However, 3.8796 times 10 to the 12 is not equal to 7.62322 times 10 to the 12 newtons. This shows us that the comet is not indeed in circular orbit. So the orbital period is given by this formula. This is just Kepler's third law, that t squared over r cubed is the same for any two objects orbiting the same body. So we're giving that the orbital radius of the comet is 18 RE, where RE is the mean orbital radius of the Earth. So we know that the orbital radius of the Earth or the orbital period of the Earth is 1 year. And I mean, technically this formula is for SI units, but they're just constants, so it's not going to matter. Like the conversion factors are just going to be constants. So I'm just going to write it as 1 squared is going to be equal to KRE squared, E cubed. So 18 RE cubed times K is going to equal to the period squared. So that's going to be 18 cubed RE cubed, 18 KRE cubed equal to T squared. We know that this is equal to 1. So 18 cubed equals T squared. So T is going to be the square root of 18 cubed, which is, let's see, now the square root of 18 cubed, which is 76.3675 years. The quantities in this question, the quantities like this have been given in 2SF, so I'm just going to give this in 2SF as 76 years. All right. Next, the total energy of the comet is the sum of its kinetic and its gravitational potential energy. We need to show that this energy. So this is just annoying. Anyway, let's get on. So the kinetic energy is 1/2 mv squared, which will be 1/2 times 2.242 times 10 to the 14 kilograms times its velocity, which is 5.457 times 10 to the 10, I think it was. No, it was 10 to the 4 squared. This is going to be equal to, let's see what's going to be equal to. So it's going to be equal to 1/2 times 2.242 times 10 to the 14 times 5.457 times 10 to the 4 squared, which is equal to 3.33821 times 10 to the 23 joules. The potential energy is going to be equal to, the gravitational potential is going to be equal to negative GMM over R. That's the formula. So it's going to be negative 6.67 times 10 to the negative 11 times, that's G, times the mass of the sun, which is, God, this is, times the mass of the sun, which is 1.99 times 10 to the 30, 0.99 times 10 to the 30, times the mass of the comet, which was 2.242 times 10 to the 14, all divided by the distance to the sun, which is 8.758 times 10 to the 10 meters, which is going to be equal to, so it's going to be equal to negative 6.67 times 10 to the negative 11 times 1.99 times 10 to the 30 times 2.242 times 10 to the 14, all divided by 8.758 times 10 to the 10, which gives us negative 3.39789 times 10 to the 23 joules. Adding the two up, which I'm just going to write like this, kinetic energy plus potential energy is going to be equal to, let's see, it's equal to negative 5.96831 times 10 to the 21 joules, which is indeed approximately negative 6 times 10 to the 21 joules. Calculations for a different comet show that it has total energy of 6 times 10 to the 21 joules at its closest point to the sun, and the students suggest that its comet will not remain in orbit. So, okay, so here the suggestion is correct. The suggestion is correct. And here's the reason. So any body that's orbiting or not will have a kinetic energy and a potential energy. So the potential energy is negative, the kinetic energy is positive. If the body has if this kinetic energy is less than the absolute value of this potential energy, then the body will remain in orbit. For the body to escape from orbit to infinity, so I guess to move from orbit to infinity, it has to have a kinetic energy equal to the value of the potential energy. Well, absolutely equal to the value of the potential energy, at which this total energy will be 0. So any energy higher than that, so any energy higher than 0, means the body will escape orbit, since the kinetic energy is higher than the gravitational potential energy. If the gravitational potential energy, if the total energy is negative like it is here, then that means the body doesn't have enough kinetic energy to escape orbit. So it cannot overcome the gravitational potential energy. You can write this if you want. I'm not gonna write it. Yeah, okay. Let's continue on with this question. Here we have the moon and the earth, which the earth has a mass of 81 times that of the moon. And we're asked to find at which point the gravitational potential is maximum. So let this be the moon with mass m, and let this be the point with the earth with mass 81m. And basically there's going to be some point within this P that's going to have the maximum gravitational potential. And we want to find the ratio between this distance and this distance. Now here's the thing, this is kind of a calculus question. I mean, not really. Maybe I'm going to solve it with calculus. So we know if the gravitational potential energy is maximum at point P, and the change of the gravitational potential with respect to the position is going to be equal to 0. But we know this value to be equal to negative g, the gravitational field strength at that point. So we want this to be equal to 0. You can think of this as like if you draw like the equipotential lines around these. So if, for example, if you ignore the earth right here, the equipotential lines around the moon would be circular like this. However, because the earth is there, it's going to be like this weird eccentric circular orbit, such that at P it's going to be horizontal like this, and it's going to be returned to being circular like this at the earth. If you think of these like as like hills, or I guess like potential wells, so at P the potential is going to go to negative infinity, so it will also do that at earth, at not P, at the moon, like this. So at P this will have a slope of 0, so the tangent will be 0. Anyway, so at this point, the change in the potential with respect to the change in x must be equal to 0, and this is equal to negative g. So g must equal 0. So the gravitational field strength must equal 0. If so, the gravitational field strength from the moon will be this gm over this distance squared. So this distance squared, I'm gonna call this distance x and this distance y. So this will be gmm x squared, and this will be g times 81m over y squared. So these two must be equal. So that gives us that x. That gives us that if x equals k. If x equals k, then y must equal 9k. So that y squared is 81k squared, so that these two cancel out. So we want the distance from P to the Earth, which is y over x. So that will be 9k over k, which will be 9. All right, here's another question. So we're giving details about a moon and a lunar prospector that is, I think, orbiting the moon. Yeah, it has an orbit radius of that. And we need to calculate the acceleration of the orbit. So the acceleration is going to be equal to, so in orbit, the acceleration is equal to the centripetal acceleration, which is going to be equal to gm over r squared. So the gravitational field strength. You can also show this by the force is gmm over r squared, which is going to be equal to F, which is going to be equal to mg, so that the m's cancel out. So g is equal to gm over r squared, which is going to be equal to 6.67 times 10 to the negative 11 times the mass of the moon, not the lunar prospector, which is 7.348 times 10 to the 22 divided by the orbital radius, not the radius of the moon. So 1.84 times 10 to the 6 squared. Let me just put that into my TI. This topic is very annoying and it's gonna be just stupid. I hate that. Times 10 to the 22, all divided by 1.84 times 10 to the 6 squared, which gives us that's low. That's 1.44764 meters per second squared. So that will be in 3SF. That will be 1.45. Calculate the orbital period of the lunar prospector in this orbit. So the centripetal acceleration g here is going to be equal to omega squared r. This is because this is just the formula. And then the period is going to be equal to 2 pi over, it's going to be equal to, it's going to be equal to 2 pi over omega. Because the omega is the radians per second, so 2 pi radians divided by the radians per second is going to give us the time it takes to travel the 2 pi radians. So omega from this is simply g over r square rooted, which will be, that'll be low down, right? That's pretty slow. So that'll be 1.447464 whatever, divided by the radius, which is 1.84 times 10 to the 6. So that will be that divided by 1.84 times 10 to the 6, which is that is really slow. That was 8.8699 something. Yeah, sure. That times 10 to the negative 4 hertz, and or radians per second squared. Oh god, radians per second squared is a more accurate units for this, I guess. And t is going to be 2 pi over omega, which will be equal to, let's see, so 2 times pi divided by that gives us 7,083.68 seconds. So that's the orbital period. Those 3SF, that would be 7,080 seconds. I think that's good enough. Next, the lunar prospector was moved to a different orbit where its gravitational potential energy was this value. And we want to calculate the height above the moon's surface of this different orbit. So the gravitational potential energy, UE, is equal to negative gmm over r. Here r is the orbital radius. Now here's the thing. If we consider the moon as a point mass, then the orbital radius is going to be from the lunar prospector to the center of the moon. So this length right here is r. We want to find the height above the moon's surface, which is this, so this h. So from the radius, we have to subtract the radius of the moon, which is this value. All right, so this is going to be equal to, anyway, to find the radius from this, we can just say that r is negative gmm over ue, which is going to be negative 6.67 times 10 to the negative 11 times the mass of the moon, which is 7.34 times 10, which what was that, so 22 times to 1.263 times 10 to the 2 divided by UE, which is negative 3.47 times 10 to the 8. That's all good. I'm so tired. 6.67 times into negative 11 times 7.348 times 10 to the 22 times 1.263 times 10 squared, all divided by negative 3.47 times 10 to the 8, which gives us 1.78389 times 10 to the 6 meters. So from r, we can subtract the radius of the moon to get h, which is going to be equal to 1.78389 times 10 to the 6 minus the radius of the moon, which is 1.737 times 10 to the 6, I think, yeah, times 10 to the 6. So that will equal, let's see if that will equal that minus 1.737 times 10 to the 6, which is going to be equal to 46,893.2, I think. 46,893, yeah. And that's the height. So to 3SF, that would be 47,000 meters. Okay, so next, the speed of the lunar prospector in orbit was 1.66 kilometers per second. And the lunar prospector left orbit and crashed onto the surface of the moon. And want to calculate the kinetic energy of the lunar prospector. So this is just a conservation of energy question. So at orbit, it has a kinetic energy and a potential energy at orbit. So kinetic energy and UE. And at the surface, it will have also a potential energy and a kinetic energy. Yeah, and you want to find the kinetic energy at the surface, we have to subtract we have to first find the total energy in the orbit and subtract the energy in the potential energy at the surface of the moon. So the kinetic energy at the orbit is going to be 1/2 mv squared, which is going to be 1/2 times the mass, which is the mass of the lunar prospector, which is 1.263 times 10 to the 2, 10 to the 2, times the velocity squared. The velocity is 1.66 times 10 to the 3 meters per second. Has to be SI. Remember that. This is equal to, let's see, what's that equal to? 1 divided by 2 times 1.263 times 10 squared times 1.66 times 10 to the 3 squared, which gives us 1.74016 times 10 to the 8 joules. The potential energy at orbit is negative 3.47 times 10 to the 8. The potential energy at the surface is going to be, let's see, so at the surface, the distance from the center of the moon, which we're assuming as a point mass again, is going to be the radius. So that's simply going to be negative gmm divided by the radius of the moon, which is so annoying. Negative 6.67 times 10 to the negative 11 times the mass of the moon, which is 7.348 times 10 to the 12 or 22 times the mass of the thing, which is 1.263 times 10 to the 2 divided by the radius of the moon, which is 1.737 times 10 to the 6 meters, I think, right? Yeah, okay. So this is equal to so annoying. Negative 6.67 times 10 to the negative 11 times 7.348 times 10 to the 22 times 1.263 times 10 squared divided by 1.737 times 10 to the 6, which is negative, oh my god, my voice is dying, which is anyway negative 3.56368 times 10 to the 8 joules. So now the kinetic energy plus the potential energy at orbit minus the potential energy at the surface will be, let's see, it will be, so that'll be 1.74016 times 10 to the 8 plus negative 3.47 times 10 to the 8 and minus negative that value, whatever, which gives us the answer of 1.83384 times 10 to the 8 joules, which to 3SF is 1.83 times 10 to the 8. I have to drink some water. I am dying. Oh my god. Right. So there are variations in the density of the material of the surface of the moon. Measurements of the lunar prospector in orbit were used to detect these variations. At one point in its orbit, the lunar prospector passed over a region where the density of the surface was greater than average. Suggests how this affected the centripetal acceleration of the lunar prospector. So at a region where the density is higher, so more mass is concentrated, that means the gravitational pull is going to be higher. So the gravitational field strength, G, will be higher, which is the centripetal acceleration. So that will increase the centripetal acceleration. You can write this down. I am honestly too lazy, so yeah. Alright, so here's another question. One of the moons of the Jupiter, the planet Jupiter, is named Io, and we are given the mass and the gravitational potential due to Io at its surface is that. State what is meant by a gravitational potential of that. So, okay, so the gravitational potential is the work done per unit mass, to move an object from the surface of Io, to infinity is negative 3.27 times 10 to the 6 joule per kilogram. That is the meaning, that is the definition of gravitational potential, and that's what this question is asking for. So now it wants us to show that the radius of Io is approximately equal to that. So V, the potential, is going to be equal to negative Gm over R. So this means that R is negative Gm over V, which is going to be equal to, let's see, so that's negative 6.67 times 10 to the negative 11 times the mass of Io, which is, Io is not written capitally, I'm stupid. 8.93 times 10 to the 22 kilograms divided by the potential, which is negative 3.27 times 10 to the 6 joule per kilograms. This will give us, this will give us negative 6.67 times 10 to the negative 11 times 8.93 times 10 to the 22, all divided by what? Divided by negative 3.27 times 10 to the 6th, which will give us 1.8215 times 10 to the 6 meters, which is indeed approximately 1.8 times 10 to the 6 meters, right? So next, a volcanic rock of mass 3 kilograms is ejected vertically upwards from the surface of Io with an initial velocity of 760 meters squared. The rock reaches a maximum height h above the surface of Io, and we need to show what the rock's gravitational potential energy at h is. So the kinetic energy at h is equal to 0. So kinetic energy at h is equal to 0, meaning the potential energy, the gravitational potential energy at h is going to be equal to the potential energy at the surface plus the kinetic energy at the surface. So the kinetic energy at the surface is equal to 1/2 mv squared, which is going to be 1/2 times 3 kilograms times 760 squared, which will be, let's see what it will be. It will be 1/2 times 3 times 760 squared. That will give us 866,400 joules. The potential energy at the surface is going to be equal to negative G. No, it's not going to be equal to. It's going to be the gravitational potential is already given, so we can just calculate that. I mean, you can negative GMM over R it, but this is also easier. God. So it's simply going to be equal to M times the potential, which is going to be equal to 3 kilograms. So 3 kilograms times negative 3.27 times 10 to the 6 joule per kilograms, which will make us 3 times negative 3.27 times 10 to the 6th, make us negative 9.81 times 10 to the 6th. So the potential energy at H will be equal to 866,400 joules minus 9.8 times 10 to the 6 joules, 9.81. This will be equal to that plus that, so that will give us negative 8.9436 times 10 to the 6 joules. Now, a kilojoule is 10 to the 3 joules, and a megajoule is 10 to the 6 joules. A gigajoule is 10 to the 9 joules, and so on. So this is going to be equal to negative 8.9436 times megajoules, because 10 to the 3, which is indeed approximately negative 9 megajoules. Right. So next we need to calculate H. So at H, at a height H above Io's surface, its distance to Io's center is going to be wait, are we even given the radius? Yeah, we found the radius. Is going to be h plus r. So negative gmm divided by r plus h is going to be equal to negative 9 megajoules, or whatever, the gravitational potential energy at h. So we can quickly find r plus h as negative 6.67 times 10 to the negative 11 times the mass of IO, which is 8.93, times 10 to the 22, I think, yeah, okay. Times the mass of the rock, which is 3 kilograms, all divided by the potential energy at h, which is negative 8.9436, yeah, that times 10 to the 6, which will give us, let's see what it will give us. Negative 6.67 times 10 to the negative 11 times 8.93 times yeah, 10 to the 22 times 3 divided by negative 8.9436. Oh no, we already found that. I don't need to write that. Just for this. That gives us 1.999796 times 10 to the 6 meters. So h is going to be that plus r plus h minus r. So I'll be 1.99796 times 10 to the 6 minus the radius we found as 1.8215 times 10 to the 6th, which will be, so that minus this value we found will be, that's really large. Well, okay, 176,456 meters. So our answer is going to be, what is it going to be? It's going to be at 3SF, I would say. Is it 3SF? Yeah, sure, whatever. 176,000 meters. So another rock of greater mass is ejected vertically upwards from the surface with the same initial velocity. State and explain how the height reached by the rock is the rock of greater mass compares to h. So now it will not change. So the height doesn't change. And the reason is that h is given by the equation, so 1/2 mv squared plus its plus the I can't talk, plus the potential at the surface, which is negative gm m over r, which is going to be equal to the potential at h, which is going to be negative gmm over r plus h. And as you can see, m's cancel out. We get 1/2 v squared minus gm over r is going to be equal to negative gm over r plus h. Hence, okay, I can't English. Since the mass cancels out, h doesn't depend on the mass. Depend on the mass of the object released, or the what object? Of the objects ejected. Yeah, okay, but I'm so tired. I'm just gonna. That's it for this one. All right, so now let's get to some material questions. Now, unfortunately, I don't have the material paper you guys have. Make sure to solve those questions because they will appear in the exam. But I'm just gonna solve a couple, and I'm gonna solve like easy questions, questions that don't take 3 years, but like, instead like contain some stupid detail that nobody cares about. I'm gonna be solving those. So the unit of tensile stress, that is, so tensile stress is tension over the area, which is newtons over meter squared, or pascals if you want. But it wants it in fundamental units. So newtons in fundamental units is kilograms meters per second squared, because that's F equals ma, divided by meters squared. So it'll be kilograms per meter per second squared. So the answer is kilograms per meter per second squared. Next, we are given a stress strain graph for materials X and Y. This is the one for X. Now material Y is brittle. Material Y has a greater Young's modulus than X and has the same breaking stress as X. So we need to understand what all of these mean. So a brittle material is a material that cannot extend much beyond, cannot extend like to a yield point before it breaks. So it barely extends beyond the elastic limit before it breaks. So its graph is usually something like this. Its graph is usually just linear and then maybe a little bit at the end before it breaks. That's what brittle means. The material that's not brittle would be ductile, and a ductile material is one that goes beyond the first yield point. So it would be something like this. It could be something like this. It doesn't matter. And the more the material extends is before breaking, makes the material more ductile. For us, however, it's going to be something like this. Now, a greater Young's modulus means it's going to have a greater slope before hitting the limit of proportionality. So we want to have a higher slope than this. So it'll be something like this, probably. And this determines the stiffness of the material. The higher the slope, the higher the stiffness. So the higher the Young's modulus, the higher the Young's modulus. And it has the same breaking stress as X, which means it breaks at the same stress as X, which is at this line. So it'll be something like this, probably. That's what this question wants. I think you can draw like a little bit of disproportionality at the end, but it doesn't matter. All right, let's continue with this question. So you have an object of 2.7 kilograms hanging on like this. So now let's look at all the forces acting at this point. So we have the weight, which is going to be 2.7 times 9.81, which is equal to 26.487 newtons. And we're going to have tension forces acting like this and like this. And he's going to have a horizontal and a vertical component like these. The horizontal components cancel out and the vertical components add up to make the weight equally. So that means one of the horizontal components must be half of the weight. So this angle right here is 60 degrees, and so is this angle. So this is t times the sine of 60 degrees. So t sine of 60 degrees is equal to mg halves, which means t is going to be equal to that divided by 2, so 26.487 divided by 2 sine 60, which will give us, let's see what that will give us. I'll give us 15.2923 newtons, which to 3SF is 15.3 newtons. So the strain in each string is 1.5 times 10 to the negative 2. That'll give us a cross-sectional area of, and that too, okay. So the Young's modulus is the stress over the strain, which will be, the stress is the tension over the area, and we have the strain as well. So this is going to be equal to the tension, which is 15.2923 newtons, divided by the strain, which is 1.5 times 10 to the negative 2. Strain is unitless, remember that, or dimensionless. Now we need to convert the area into meters squared. So 1 millimeter is 10 to the negative 3 meters. Pardon. So 1 millimeter squared is 10 to the negative 3 meters squared, or negative 6 meters squared. That will be 0.75 times 10 to the negative 6 meters squared, which will give us, let's see what that will give us, divided by 1.5 times 10 to the negative 2 times 0.75 times 10 to the negative 6, which will give us 1.35931 times 10 to the 9 pascals. So 3SF, that will be 1.36 times 10 to the 6. Though I guess it's not right to use 3SF here because this is 2SF, so I'm going to write that to 2SF as 1.4 times 10 to the negative 9 meter pascals. Or not 9, positive 9. That's it for this question. Alright, so there are 3 questions about things here. I'm not going to solve the last one. It's whatever. Okay. Well, anyway, so let's begin with the first one. Which is always the property of a brittle solid. So again, remember the definition of brittleness. Brittle means it cannot extend a lot beyond the limit of proportionality. So after it goes to the limit of proportionality, it might extend a little bit. It might extend a teeny tiny bit after the elastic limit, but it will break after that. This doesn't imply it has high stiffness, doesn't imply it has low breaking stress either. It could be really high, but still have that. It doesn't imply it has little elastic strain energy, but it does imply it undergoes little plastic deformation because it can't go too beyond the any elastic limit, so it can't reach any yield point, so it doesn't have that much plastic deformation. Now, if you're asking what plastic deformation means, you also need to know that. You have to remember, elastic means that the object can go back to its initial shape and size after the tensile forces are removed, or the compressive force, I guess. I guess the deformative forces, we can call them. And plastic is the opposite of that. So plastic for objects, when an object is facing plastic deformation, it cannot go back to its initial shape and size after the forces are lifted. This means now there's an elastic limit before which the object is elastically deformed, and afterwards which the object is plastically deformed. For us, a brittle solid barely goes beyond the elastic limit, so it barely undergoes any plastic deformation. Which quantity is given by the area under the stress-strain graph? Now, you can have 2 types of graphs in this topic. Those are the extension or the tension to extension graphs, which will be linear until it's not. So this will have, so the relation here is T equals K delta L. This is Hooke's law. And the most important thing about this graph probably is that the area under it is the energy, the elastic potential energy stored in the thing. However, we also have stress strain graphs. So the stress strain graphs like this, they'll be like this, and the energy, the area under this, if you to find what that means, you can look at the units. So this has units Pascal, this is dimensionless. So if you multiply pascals by dimensionless, or to find the area like this, I guess, so the area, so the area has units pascals. Now you might ask, then doesn't the area give some sort of pressure? Well, usually you take this as newtons per meter squared, which is equal to Newton meters per meter cubed, which is equal to joules per meter cubed, which is the energy stored per unit volume, or the work done per unit volume for that point. So that's what this graph gives. This is a Young's modulus question. Now, this is just, it's guaranteed like that a question like this will appear. You just have to know what the ratios are. So the Young's modulus is sigma over epsilon, which is equal to T over A, and epsilon is delta L over L. So this will be times L over delta L, which is equal to TL A delta L. You have to know this. There's also the stiffness K, which is T over delta L. So you can notice how there is T over delta L here. So you can say that E is equal to KL over A. This is and you can if you say that the Young's modulus is unique for a material in a given shape, you can say that K is inversely proportional with L, the length, and is inversely proportional, is directly proportional with the cross-sectional area. And yeah, basically any question. Oh, there's also the energy as well. So the elastic potential energy E, which is different from the Young's modulus, is 1/2 kx squared. This is also 1/2. This is also 2 t squared over 2k. These are all ratios and formulas you need to know. You don't memorize them, but you can derive all of them once you need them. And you will be asked basic questions depending on those ratios. So you should know them. I'm not going to solve this question, but just know them. Anyway, that's it for this one. Again, let's quickly solve this question. So we have a force extension graph, and the forces gradually increase from 0. This is the loading curve, and then reduce back to 0. So this will be the unloading curve. However, the force extension curve is the same during loading and unloading. So the graph goes like this and then goes back like this in the same direction. So what is the behavior of the wire between OX and X and Y? So here's the thing. Here we can say that X is the limit of proportionality. We can't really comment anything on Y, but the important thing is that you need to remember the definitions of elastic and plastic. Remember, if the object can go back to its initial shape and size, it's elastic. And here, the force and extension curve is the same during loading and unloading. This means at both X and Y, the object is elastic. If, for example, the object was plastic between X and Y, I guess plastic deformation was being applied between X and Y, then after the forces were lifted off, so during unloading, the graph would be something like this. And there would be some permanent extension that the plastic deformation caused, since the object couldn't go back to its initial shape and size. However, if both of these go back to their initial shape and size, that means at both points, they're elastic. That's it for this question.